All right. Well, like many people before me, I'm sure. Okay, this is, I don't know why I can't move. I can't change slides. Oh, gosh. Sorry, I'm having a technical problem. Give me 1 second. Okay, I think it should be okay. I'm having problems with the PDF. I'm not sure why not. Is this readable as it is?
Yeah,
Hello?
yes.
Okay, good. Thank you. Thank you. So, yeah, thank you. Thank you for inviting me. It's a great honor. I'm sure a lot of people have said a lot of things about Rodney already. I thought I would just add one thing. What influenced me the most in all his work was not so much his work, but his personality. Especially, strangely enough, I guess the preface to his book, which I read as a very young student. At the time, I was kind of pulled into becoming a particle phenomenologist, which would certainly have been very frustrating for me and for the others. But luckily, at some point, I found his book, and among many things in his book, what I really loved was the introduction and this sentence, which I'm sure everybody knows, that they are down to earth physicists and chemists who reject lattice models as being unrealistic. In its most extreme form, their argument is that if a model can be solved exactly, it must be pathological. I think this is defeatist nonsense. I really loved this sentence, and to me, it really summarizes the man, absolutely fearless, cheerful, with a good sense of humor, and of course, a complete genius. So there it is. That's my homage to him. Now let's cut to the chase and move to the talk itself. This is based on an unpublished work with my collaborator Nick Reed. It's going to appear in the next couple of weeks. And that's something about XXX spin chains, yet again, this time from a slightly more fancy point of view, maybe, which is the point of view of anomalies, what I would call toothed anomalies, but my Dutch colleagues called me and say this should be called uithoofd anomalies, so there they are, and the related O3 sigma model. So this is a topic that's a little bit away from, I think, the core of the conscience. As a result, the talk will be very pedagogical and there will be very few technicalities. So let me start with the context and the motivation. What is a uithoofd anomaly and why are they interesting? So the best way to explain this is to think, there's going to be a bit of conformal field theory, to think about what's called the SU2 level 1 Vesumino model, which is one of the simplest solved rational conformal field theory. And as discovered by Gepner and Witten in 1986, this model has an anomaly. Now, what does it mean? The model has a Z2 symmetry, which means the action is invariant under the symmetry G goes to minus G, where G is the matrix field in the model. So it's not anomalous in the usual sense, but the point of the uithoofd anomaly is that this symmetry cannot be gauged. What it means in practice is that if you try to define your model on a torus with Z2 twisted boundary conditions, you encounter ambiguities. Let me try to explain what the ambiguities are. So the partition function of this model on a torus with doubly periodic boundary conditions is very well known. It's just the sum of the moduli squares of two characters, the identity character and the spin, the matrix field character. And then if you want to define twisted boundary conditions, the simplest you can do is take a model that's periodic in the space direction and anti-periodic in the time direction. So when you trace, you put a -1 whenever you have a field that's odd under the Z2 symmetry. Now, the identity, of course, is even, and the G matrix field is odd. So what you get is a new partition function, which I would call PA, A in the time direction, which is the difference chi0 square minus chi1 half square. Now, this is very well known. Everybody can do this. We are used to doing this for the Ising model, or say for the free boson when you define what's called the Z2 orbifold of the free boson. Now, once you have ZPA, you can get all the other partition functions using the modular group. The simplest of all is to get ZAP. To do that, you exchange space and time, and you can use the standard formulas for modular transformations of characters of the Kac-Moody algebra in that case, and you get that ZAP is chi0 chi1 half bar plus chi1 half chi0 bar. Fine. Finally, what you want is the doubly anti-periodic case, and that should be easy to get. For instance, what you get is start with ZAP, and now change the modulus of the torus tau into tau plus 1. So now time direction means propagating in the vertical direction on my slide, and then again in the horizontal direction. That's why you get ZAA. But when you do this calculation, you get a slightly strange result. You get minus I chi0 chi bar 1 half minus chi1 half chi bar 0, okay? And then you can argue, well, if I do T twice, I will encounter the anti-periodic boundary condition twice, so I should go back to ZAP. In other words, we would expect that T square ZAP, which is T square of SZPA, should be SZPA. But bizarrely, you find minus. And in fact, when you keep playing this game, you realize that the signs of the partition functions are not well defined. If you impose any anti-periodic boundary condition on the system, and then try to use the modular group to calculate all the other partition functions in a consistent way, so that anti-periodic twice is the same as periodic, because -1 square is equal to +1, you encounter, like I said, bizarre results. Bizarre results mean that the sign of the partition functions is not well defined. So if you try to define the Z2 orbifold theory corresponding to the Ves-Zumino model, you encounter a paradox. There is no such theory, and that is what is called the 't-Hooft anomaly. The Z2 is there, but you cannot gauge it. Now, these anomalies have become very fashionable lately, in particular because they are known to be preserved by the renormalization group, which means if you have an anomaly in the UV, you should have the same in the infrared. If you have an anomaly in the infrared, you have the same, should have the same in the UV. So the purpose of my talk is really to start with this anomaly in the Ves-Zumino model and ask myself, what do we know about the Ves-Zumino model from the point of view of conformal field theory and lattice models? Well, we know a lot because thanks to the work of Affleck, Haldane, and the Zamolodchikovs, we know, first of all, that the Ves-Zumino model is the infrared fixed point of the O3 sigma model at theta equals pi. Okay, so that's the first point. The first thing that would be interesting in this context is to ask ourselves, what is the interpretation of the anomaly in the O3 sigma model? By the way, an important remark is that the O3 sigma model is badly named. It doesn't have O3 symmetry in general. It has only SO3 symmetry, rotations of the n vector. O3 is made of rotations and inversion. N goes into -n. And while the kinetic term of the model is, of course, invariant under inversion, we see that the topological term is not. It is not except when theta is equal to 0 and when theta is equal to pi. When theta is equal to pi, even though changing n into minus n changes the sign of the topological term. Because of the equivalence, theta goes into theta plus 2 pi, minus pi is equivalent to plus pi. That's why we're having this extra symmetry at theta equals 0 and theta equals pi. Other than this, the model is really only an SO3 sigma model. And now it's also easy to argue that inversion in the Vesuminor model corresponds to, that the Z2 symmetry of the Vesuminor model corresponds to inversion in the O3 sigma model. So a very interesting question would be, what happens to the anomaly in the context of the O3 sigma model? However, because of the time I have, I cannot discuss this, but I can discuss something else that should be of more interest to my friends doing lattice integrable models, which is the following. We also know, thanks to the work of Haldane and others, that this O3 sigma model is nothing else but a low energy description of XXX spin chains with the correspondence that the topological angle is equal to 2 pi s. So for half-odd integer spin chains, we know that the low energy properties of the spin chain are described by the sigma model, or if you wish, in the infrared limit by the Vesuminor model. Since the 't Hooft anomaly is preserved under the RG, this means that we should be able to see this anomaly also in the context of the XXX spin chain. And that's what's really going to be the topic of this short talk. It's going to be some aspects of what is this anomaly for spin chains, okay? All right, so obvious remark before we get into this, obvious but kind of intriguing already. The spin chain has only SU2 symmetry. In fact, it's SO3 if the spin is integer. It's SO3 if the length of the chain is even, but otherwise it's SU2. There is no mention of O3. There is no mention of the inversion n into minus n in the context of the spin chain. We certainly cannot claim that n goes to minus n is realized by s goes to minus s, tempting but obviously wrong, because this map does not preserve the commutation relations of SU2. So if we don't break the SU2 symmetry, we cannot have this as the inversion. So the first question, whose answer is actually rather well known, is what is inversion in the context of the spin chain, and what does it mean that it's anomalies? All right, so now I move on to the sigma model and spin chains. Well, again, Haldane and Ian, by the way, giving this talk after Rodney's death cannot but make me think of Ian, and Ian passed away very recently also. So that's a lot of people who have gone. Anyway, these people knew that because of the map between the ON vector and the spins in the spin chain, which is roughly of the form n of x is like -1 to the L SL, and that's very easy to understand because the ground state of the Heisenberg chain is made classically of a Nail state with alternating spins. So when we map this chain to the sigma model, whose action is something like d mu n squared, the ground state should be pretty much n constant, which means, of course, that the map from S to N has to involve a -1 to the L sign, alternating. We see from this map that if we want to send n into -n, really all what we should do is translate by one side. Okay, so that's a fact that's rather well known. It's that the continuum limit of translations by one side in the spin chain gives rise, in fact, to the inversion in the sigma model. And by the way, that's what's called now, in the fancy terms of the work of Cheng and Seiberg, among others, an immanent symmetry. It's not an emergent symmetry, because an emergent symmetry is a symmetry that's there in the infrared when you throw away irrelevant operators that break the symmetry. It's something very different. It's a symmetry that's always there, but at different steps of the renormalization group, it is interpreted differently. For the lattice model, it's translation. For the continuum limit, it becomes inversion. I'm not really sure what it becomes in between, but that's not the point. So all this to say that if we want to understand inversion in the spin chain and its anomaly, we should really think of what is the equivalent of Z2 twisted partition function in the context of the lattice model. But if Z2 symmetry corresponds to translation, what we should do, therefore, is consider spin chains of odd length. So that's really the heart of my talk. It is Heisenberg spin chains of odd length, a very old topic that's been studied by many people, including in the context of the eight-vertex model by Baxter and Bajanov, by the way. But here I thought I would just allude to one reference, which is the paper of Fabricius and co-workers, where they just decided to solve numerically and by Bethe-Ansatz spin chains of length between 12 and 16 sites, and they observed, like many others before them, that there's something a little weird in the case of odd length. In particular, it's kind of hard to see the result of the conformal field theory. There are weird degeneracies, and the ground states have weird values of the momentum. So that's what I want to explain. I want to see how this is related with anomalies. That's a rather large topic, actually. I will only discuss it using a very specific approach, which is the semi-classical approach. So let me just babble a bit about odd length Heisenberg spin chains. And I always have in mind, although I may not repeat it systematically, half-odd integer spin. Okay, so let's take an odd length spin chain. Well, actually, let's take an even length spin chain to start. Even length spin chain has a very straightforward ground state, alternating spins, right? Nail state. If you take an odd length spin chain, you encounter a problem with your nail state, because if you start with up, you go down, you go up, and then when you go around the spin chain, because it has an odd length, you seemingly come back having two spins that are parallel, which is not possible. To do the classical ground state, you need to twist this a little bit. So the classical ground state has the shape that I illustrate here for 15 sites. It is almost a sequence of anti-parallel spins, but on top of this, you must have a slight rotation, so that after you've gone around the whole system, you manage to have periodic boundary conditions for your spins instead of having anti-periodic boundary conditions. Okay, so that's rather clear, well known. And there is a nice way to describe this mathematically, maybe not really necessary for my talk, but why not? It is the following. You label the spins by L. L is running from 0 to n minus 1. So say in this example, n equals 7. So n minus 1 is 6. I have spin 0, 1, 2, 3, 4, 5, 6. And then I'm going to define a new variable, L twiddle, which is defined, in fact, it's a bijection, so that L is equal to 2L twiddle mod n. Let's write an example for n equals 7. I didn't do 15 because it's just too many rows in my table. L equals 0, L twiddle equals 0, L equals 2, L twiddle equals 1, L equals 4, L twiddle equals 2, L equals 6, X twiddle equals 3. You see that when you go over the even sites, L twiddle increases by 1 every time L increases by 2. And then you go around your system and you carry on. L equals 1, L twiddle equals 5. L equals 3, L twiddle equals 5. Okay, so you have 1, 3, and 5. So you have 4 even values of L twiddle, 3 odd values of L twiddle. And now there's a convenient way to write the ground state. I parameterize my vectors by cosine L twiddle of L and sinus L twiddle of L times theta 2, where theta 2 is 2 pi over n. A very, very fancy way of saying nothing else but the fact that when I go from one spin to the other, I rotate by pi plus pi over 7. Okay? But because 2 pi is equivalent to 0, careful in SO3, I can take the cosine of pi plus pi over 7, pi plus 3 pi over 7, pi plus 5 pi over 7, etc. Okay? So this is my classical ground state. By the way, a slightly fancy remark, but it's very useful. If you think of the classical ground state for the even chain, it is parameterized simply by the vector of the nail state, so that the first vector you take, and then all the others are obtained by alternating. Now, the vector defines a point on the sphere. In other words, the ground states for the even case are parameterized by the sphere S2. In contrast, for the odd chain, not only do you have the direction of the first vector, but you also have to decide in which direction you're tilting the next vector with respect to the first one. So you have not only S2, but also angles around S2. That means you have SO3. So the space of ground states for even and odd chain is parameterized by different manifolds. In the case of the odd chain, it's SO3. Now, let me focus a little bit. What is it that we learn with semi-classical quantization? What we learn is that once we have a classical ground state, we can build a approximate ground state of the quantum system, good at large spins, by building a corresponding quantum state, which is obtained by taking coherent states, right? So coherent states for spins are, for instance, obtained in the following way. If you want the coherent state corresponding to a classical spin pointing in the one direction, what you do is you build an eigenstate of the S1 component of the spin, so that n dot S1 is equal to S1. In other words, you quantize in the one direction, and you take a state whose spin in the one direction is equal to S, and that's how you obtain the coherent state for quantum spin chains. So to build your semi-classical ground state, what you can do is first take this coherent state 1 for all the spins in the spin chain, and then rotate them by the appropriate rotation, which is, of course, obtained by, therefore, taking all these coherent states, all pointing into the one direction for every spin, and then for every spin, rotating by the rotation operator in the spin S representation of SU2, if S is half integer, which is the exponential of the same angle I had here, SL3, because I've decided in my example that the spins lie in the 1-2 plane, so I rotate by S3, and I take the product. Okay, this is the coherent state associated with the classical ground state I have chosen, and then I can get all my other semi-classical ground states, there's an infinity of them, by acting with an SO3 rotation. And now I'm getting to something that's completely obvious to most of you, I'm sure. What is the effect of a translation on this semi-classical ground state? Well, a translation sends spin 0 to spin 1, spin 1 to spin 2, spin 2 to spin 3, and so on and so forth. So how do I realize this on my semi-classical ground state? Very easy. When I take the spin 0 and I send it to spin 1, I should, in order to match the ground state I want, I should rotate it by pi plus pi over 7. Okay? To send the spin 1 to spin 2, I should rotate it by pi plus pi over 7 minus 2 pi, and so on and so forth. So as a result, the translation of the semi-classical ground state is a product of translations for each of the individual spins, where for a certain number of them, namely those who had an L-twiddle 0, 1, 2, or 3, I must rotate by pi plus pi over 7. And for those who had a L-twiddle equal to 4, 5, or 6, I should rotate by pi plus pi over 7 minus 2 pi. Now, this sounds like a complete bunch of tautologies, but the point is that for half integer spins, we're having SU2. So for half integer spin, a rotation of 2 pi is not trivial. A rotation of 2 pi results in an additional -1. So whenever I translate the ground state for half odd integer spin and odd length, I have to pay the price, so to speak, of 2 pi rotations for a number of spins, which is n+1/2. Therefore, I can write the result of the translation of my ground state as follows. I have the rotation of all these spins, which I can always write as an exponential of j free, the total rotation in the free direction, of an angle, in that case, pi plus pi over 7, in general, plus pi plus pi over n. And on top of it, I have a -1 to the n+1s. Okay, this sign is crucial because this is what's going to give us, in fact, the anomaly. Okay, so now let's move back a little bit to the idea of semi-quantization. What you do when you have semi-quantization is you ask yourself for the happens to the quantum mechanics of the collective degree of freedom that represents your spin. This is also what's sometimes called mini superspace approach. You neglect fluctuations in the space direction. You represent all your spins by a collective state, and you wonder what is the quantum dynamics of that collective state. For the case of even spin chains of even length, what you would get is the quantum mechanics of a point on the sphere. Fine. What you get in the case of odd length spin chains is quantum dynamics of a vector in SO3, which is nothing else but quantum mechanics of a rigid body. So important message, which I think very few people had actually realized it, that the semi-classical quantization of Heisenberg chains of odd length is quantum mechanics of the rigid body. Plus, if the spin is half integer, is quantum mechanics of the rigid body with a Berry phase because of that term here. So now when you do quantum mechanics of the rigid body, I know this part is going to be a little hard, but then I'm going to go back to elementary stuff. When you do quantum mechanics of the rigid body, in general, you have an energy that depends on two quantum numbers. There is the quantum numbers of the global rotations. The SO3 symmetry is not broken. There is a J for that. But then there's also the quantum numbers associated with the rotations of the rigid body around its axis. So there are two bunches of quantum numbers. There's J, which in this context I call J left, and it's M left azimuthal number. And then there's another quantum number, M right. That's the truth of the quantum mechanics of the rigid body, which is always a little bit complicated. So this is the shape of the spectrum in the semi-classical analysis. It's a very useful shape because now I can go back to results for the finite length, finite spin chains, like those obtained by the beta-ansatz, say. In the case where S is a half odd integer, all these quantum numbers have to be half odd integers. In particular, the J of the spin chain, the one everybody would call the spin of the state, is what I call the left quantum number, and that J is a half odd integer. So in a spin chain of odd length and half odd integer spin, what I'm claiming, first of all, as a result of this semi-classical analysis, and it's something that's somewhat well known in the context of the beta-ansatz, is that all the levels in the low energy theory are degenerate 2 times 2j plus 1 times, where j is half an odd integer. And now the point, the low energy theory is very important because the results I'm going to claim do not apply to the whole spectrum. They only apply to the low energy sector, as you can realize, for instance, by taking the very highly excited state of the spin chain, which is all the spins aligned. This state is not degenerate 2 times 2j plus 1 times, it's only degenerate 2j plus 1 times. In particular, and this is what I wanted to get to, so now let me get back to what's really important. The ground state of the spin chain which is obtained for any S half an odd integer by having J equals a half, and M is plus or minus a half, is 4 times degenerate. The ground state of Heisenberg chain that odd length and half odd integer spin is 4 times degenerate. And this is really where I wanted to get to. I can calculate from this what is the lattice momentum. So now we can go back to what we know about quantum mechanics of spin chain. Imagine doing your bet on that or your numerical calculations, calculating the ground state momentum of your ground state. It means looking at how translations act on your ground state, right? And yes, somebody called? No. I have 5 more minutes. I think I'm still on time. So if I define the momentum as the eigenvalue of the translation operator as usual, what I find is that for half odd integer spin and half odd length spin chain, the ground state momentum of the spin chain is a non-trivial number, which has been observed numerically. And there's been some papers trying to prove this rigorously, but I don't think it's ever been done. And my argument is not a proof, it is a physical explanation. That momentum is weird. It is plus or minus 1 over n times pi over 2a, when n is equal to 1 mod 4, or plus or minus 1 plus 1 over n times pi over 2a, when n equals 3 mod 4. This results directly from this formula up there. And now you see that this momentum has 2 parts. One is the part scaling like 1 over n, which we know very well from conformal field theory, but on top of it, there is a finite value of the momentum. And now we are used to finite values of the momentum in condensed matter physics. We are used to having finite values of the momentum equals to pi very often. In this case, it's not pi, it's plus or minus pi over 2. So this means, in particular, that for large spin chains, tau square, translation square, acts as -1. And now you see, if you go back to the map from the spin chain to the vector in the O3 sigma model, we have the ground state n, minus n in the Néel state, so we expect the translation by 2 sides should be reduced to the identity. No, it's reduced to -1. This means that inversion square in the O3 sigma model is realized not by 1, like a normal inversion square, but by -1. This means inversion itself acts like plus or minus I. And that should ring a bell to some of you who know a bit more about group theory, because what is the situation? The situation is we had an O3 symmetry, but then because we're taking chains of half integer spin and odd length, we're having a half integer spin, which means we don't have SO3, we have a double cover of SU3, which is SU2. So if we want to implement O3, we should really face the horrible truth that we need a double cover, not of SU2, of SO3, but of O3. And now these double covers of O3 are well known. They're called the pin groups. And there's 2 of them. And in one of them, inversion square squares 2 is 1, but in the other, inversion square turns out to be -1. So inversion acts like plus or minus I. So this is really where the anomaly comes from. In the spin chain, we are not having a representation of O3, we're having a projective representation of O3 for 2 reasons. One is that we have spin a half, so rotation of 2 pi is -1, which is harmless in this context. But second, the inversion is realized by plus or minus I. And there's as many plus i's as minus i's. That's why the sign of the doubly antiperiodic partition functions is not well defined, because on some states, inversion acts as I, and some others, it acts as minus I. Okay. In contrast, for instance, for even spin chain, we wouldn't have any of these problems. For even spin chains, tau square would be equal to 1. And what would happen is that translations would have, in particular, the ground state momentum would be 0 if the length of the chain is 0 mod 4, and pi if the length of the chain is 2 mod 4. And other than this, inversion would act like -1 to the j, where j is the spin of the state. So, for instance, the vector would be odd, as expected, for chains of length 0 mod 4. But be careful, for chains of length 2 mod 4, it wouldn't be odd, it would be even, while the ground state would be odd. Okay, so I think I'm almost done. I wanted to give you a bit of pedagogy about pin groups, but I think it's a little too late. Let me just mention that the name was invented by Hubert Saleur because we have spin groups like SON. We have rotation groups like SON, and the covers are called spin groups, they're double covers. So if you go from SON to ON, it's tempted to say that you're going to go from spin groups to pin groups. That's why these things have been called pin groups. Okay. Other aspects and lessons to be learned. Therefore, okay, so let me spend 2 minutes. I think it's important to do that. First of all, we conformal field theorists and lattice people, I feel, have tended to ignore too much the finite values of lattice momentum. We've been used to thinking that, oh, lattice momentum is 2 pi over L times h minus h bar, end of story. We should be much more careful. The finite part of the lattice momentum has a meaning. This is what gives rise to its eminent symmetries. And it's really a case in point, this business of inversion in the O3 sigma model. The analysis I did is semi-classical. We could do a full quantum analysis. It's very tricky, by the way, because except for spin s equals a half, we don't have the beta ansatz. There's a whole part of this business dealing with the sigma model itself and the question of whether the sigma model, the topological term with anti-periodic boundary conditions, can be defined. That's something I'm going to get into, but it's also a very interesting question. Maybe the most interesting of all is that the semi-classical dynamics is using the semi-classical dynamics of a rigid body with a Berry phase. This means this is a top, and if you rotate your top by 2 pi around any axis, its wave function gets a -1, which is kind of weird, but not impossible. The study of inversion is just the beginning of the problem. We could also ask ourselves about reflection and time reversal symmetry, and then we could ask ourselves about generalizing the result to other groups. So in fact, there is a very simple conclusion to this analysis, is that whenever the spin chain is going to be made of a self-dual representation of an arbitrary Lie algebra, self-dual, so it's translation invariant, and can have a non-trivial low energy limit. There is an anomaly whenever the representation is quaternionic, if and only if the representation is quaternionic. So for instance, if you take SP4, the 4-dimensional representation is quaternionic, so there's an anomaly, but the vector is not, which means the spin chain with SO5 does not have an anomaly. So that's one of the conclusions. Okay, I think I'm about done, so thank you very much for your patience, and that's it.
Do we have questions? So I have a question. If you take a ground state of the XXX chain from the beta ansatz,
Yes.
so what's the property of the state with respect to?
Oh, that's exactly the result I said. So this is known from beta ansatz numerically. For maybe I should share again because I can give a reference. This is known for the beta ansatz numerically for short length spin chains. That's the work of Fabricius et al. And Karbach and Mutter. So they find values corresponding to the ones I have here. To my knowledge, there is no proof using the beta ansatz for arbitrary length, even though I think it's not very difficult. The main issue, of course, is the result for higher spin, like 3-half, 5-half, etc., where, again, there is absolutely no rigorous result and no better answers. So that's what I know.
Thank you. So if there are no more questions, let's thank the speaker again. Thanks a lot, Hubert.
Thank you. Thank you.